So in the interest of actually starting on time so we can all get out and go to this party thing afterwards, let's just get started. So my name is Heather Miller. I'm a PhD student at EPFL. I work with Martin on various things. And today I'm going to talk about some of the work that I have been doing in the last several months, which is very colorfully named Spores. The title, Towards Function Passing Style in the Age of Concurrency and Distribution. So as you might infer, the idea behind these SPORE things is to sort of make it possible to do some sort of moving functions around when you want to do things in a parallel, concurrent, or distributed environment. But before I go on about this, I have to give a shameless plug to this, the Scala workshop. If you don't know about it, it's basically the academic version of sort of Scala days, in that we publish a bunch of papers, we co-locate with an academic conference, and there's a bunch of people doing cool things that are really sort of bleeding edge with the language and libraries and other things. And at the same time, we also have a bunch of really cool industrial speakers lined up this time around. Plenty of them you probably recognize, which will be announced shortly, but it's not too far away. It's in Sweden, so if you're interested in these kind of things, consider going. So yeah, spores. I'm going to start by talking about what they are and why I think they're necessary, or why we all need them. But what I think actually is the cool part is what you can do with them. I had a demo, but actually it's just going to be an example now. But if you walk away with anything, this is the cool part of the presentation. So pay attention to that. The rest is less cool. So to start, there's these two trends that have sort of been becoming rather popular in the land of software engineering and development. So a lot of these data-centric applications have sort of come to the forefront of a lot of concerns that developers are having. A lot of applications that we care about building are typically callback heavy, need to be reactive, have a bunch of asynchronous sort of concerns. Usually you operate on like a lot of data, or asynchronous data or something like this. And at the same time, you have this huge trend towards, hey, let's do some more functional style everything. It's often a little bit more concise, correct, and there's this nice property that you typically apply functionality to immutable data, right? Which in the world of concurrency helps out because you wind up with fewer data races, for example. And the nice thing about that is that these two trends are rather complementary. So functional programming is pretty helpful in the world of this data-centric programming sort of world because of these sort of two basic ideas. One, you have this basic philosophy of applying functionality to rather transform immutable data by function application. And it follows that it simplifies reasoning about data in parallel, concurrent, distributed code because you avoid things like data races and whatnot. So as a result of sort of these two things being rather convenient at the same time, there's a million of these data parallel frameworks that have popped up over the years, over actually like the last 20 years if you look at academia too. So mostly in the world of single machine parallel concurrent sort of programming, you have things like Scala's parallel collections. Java 8 got these monadic yet optionally parallel collections recently. Then there's a bunch of other research projects out there like Intel's concurrent collections, or Haskell has this parmonad, things like that. And then on the distributed side of things, frameworks like Spark, which I hope you all heard about earlier today from Michael's talk, and MapReduce also sort of take the same data parallel approach to things. And so if that's all popular and people are doing this stuff already, then why do you necessarily need spores? You're basically moving these functions around and applying them to data. It's already fine, right? It turns out, though, that closures are actually a source of a lot of problems, especially in distributed environments. They can be pretty hairy in concurrent ones as well. But sort of the main thing that I care about, at least right now, is they're basically a huge mess to distribute. And actually, you might think, okay, well, maybe this is just a Scala problem, but it's actually a cross-paradigm problem. I mean, Haskell has problems with it. Every language has problems with it. So I'm just going to enumerate through a long list of different problems that make it difficult to distribute and to operate concurrently on data in the world of just closures as they currently are. So one, you accidentally capture this reference sometimes, which if you want to serialize a function, you can't necessarily, unless the type of this is serializable. If you're going to use Java serialization, it won't actually it won't actually do anything good at runtime. It'll just explode at runtime. And then also there's the problem where language-specific compilation schemes, this was sometimes the case for Scala. They create, just how the compiler deals with closures creates implicit references that the programmer doesn't necessarily know about to objects that also might not be serializable in the same sense that this might not be serializable. Another problem is transitive references. So you might have some crazy object graph which captures things in this transitive closure that might not be serializable, and you don't necessarily know it. Which either might not be serializable or it creates memory leaks that you don't want. Other things, if you capture, if you have a closure, which is a function that has an environment, if you end up capturing in the closure's environment some mutable data that multiple threads then operate on, then you have race conditions, and that's also not desirable. And finally, unknowingly accessing object members that aren't constant. So what does that mean? Method calls, for example. In the case that maybe you're going to move a function from one machine to another, you don't necessarily want to accidentally capture a method call that maybe has a different meaning on one machine than another. Then you have totally weird logical errors that you don't want to deal with. So these are, some of many problems that you might encounter with sort of not, the way that closures currently are. And I can, illuminate that a little bit with two small examples. So the first one, it's not really, you can think of this like full-on Spark code, takes a little bit more. But in this example, you have some class, some RDD app, which has these two values in it. Doesn't matter what they are. And then you have some method that actually, so it takes an RDD, and I'm just going to tell you what an RDD is in case you don't know. An RDD is basically like a distributed collection, so you can imagine like a distributed array or a distributed list, and you maybe want to call a map function on that, pass a function to it, and what the framework like Spark does is it takes that function and it distributes it all over the network to all the shards of data, it applies it, and then it does whatever. If it's an aggregate or something, or reduce or something like this, it maybe sends it back or whatever. It does something, but the point is that you have these many pieces of data and it sends the function around to all the shards of data, right? And you can imagine then you basically want this all to run at runtime, and one problem that could happen is this looks totally innocuous. It doesn't, there's this, okay, so your function captures this param thing, but I don't know, it looks just fine, it's just a double. But the problem actually is that this param thing actually implicitly captures, a reference to this. So it's actually this dot param. And this dot param is not serializable because my cool RDD app is not serializable because this is of type my cool RDD app. So if it was extended serializable and you use Java serialization, then it would work. But this looks this looks rather innocuous. Doesn't look like a dangerous piece of code, but it wouldn't run. Another example. So let's just say if you're familiar with Akka, you have to implement this message handler, this receive method. You might want to be processing a message called request that receives some data, and okay, this is going to take a long time to deal with this data. I don't want to tie up my actor for 10 minutes, processing this data. I want the actor to do other things, so I'm going to wrap it in the future, and then, that'll get asynchronously dealt with somewhere else. And then I want to, when I get the result back, I want to send the result back to the actor who sent me the data. Seems harmless. But the problem here, actually Akka changed this recently, but this sender method, this is actually a method. They now have parentheses here, so it's maybe more obvious that it's a method. But the point is that it wasn't necessarily obvious that you were, like what this sender meant at different times. So this is an example of this method call situation that I mentioned earlier, where basically, over time the meaning of this sender thing changes because, if the actor goes on to process the next message in the mailbox, that sender thing then represents the sender of the currently processed, or the messages currently being processed. So then if Bob sends me a message, it takes me 10 minutes to compute it, and I'm currently, and the actor is currently processing a message from Sally, and then I would basically send the result to Sally when I wanted to send it to Bob, which is also a weird logical error you don't want to deal with. So these are things where, capturing and environments and stuff create more problems than, pretty tricky problems actually. So these are sort of the motivations for, having these SPORE things. And in this talk, I'm going to talk about two types, or two varieties of them. One is proposed as a Scala improvement proposal, and the other is actually a paper that we just published, or we just got accepted for publication at eCoop this year. And it's a little bit more, it's like, spores on steroids, and that you can control sort of what they capture using the type system. But first, if you actually want to go into that in more detail than I'm going to tell you about, you're welcome to read the research paper. It's on the internet. And yeah, it's a lot of details. But first, the mainline spores that exist as this Scala improvement proposal, which is down here, if you can see it. So what are they? They aren't exactly closures. You can think of them as small units of possibly mobile functional behavior. They're more an abstraction for use in these sort of tricky scenarios. And you can, and their goal, their purpose is to try and be well-behaved closures whose environments are controlled, and that avoid the hazards which I just listed. And these hazards, of course, are memory leaks, so the race conditions I mentioned, and all of these possible serialization problems that you might run into. So what do they look like? So they exist in this thing called a spore block, and there are two parts of it. There's what we call this thing here, this val up here, is a spore header. You can have a sequence of these, as many as you want, and then the actual closure. And this spore header thing here basically represents the environment. It forces you to be explicit about the environment that you want to capture. So if you want to capture all of Wikipedia and send it over the wire, you actually have to say that here. You can't accidentally capture it. And then, basically, it only compiles if everything inside of this function is inside of its local environment. That's it. That's pretty simple. The mainline spores are just mostly syntactic. And so what does it get you, or what does it guarantee you? It guarantees you that basically all of the variables that are captured using this spore header thing, or this something called capture, I'll show you in a second, that the initializers of all these captured variables are executed the initializers are executed once, and when you create the spore, they don't, happen at different times and you don't know when. And that also these references to captured variables don't change during the execution of the spore. So the evaluation semantics, it's actually important to note that the evaluation semantics of spores and closures are actually basically the same. So if you go back to this thing and you get rid of this spore marker here, the evaluation semantics are exactly the same. We don't change how they're evaluated. We just make you use this shape because it solves a lot of problems as a first step. And also, spores and closures are related in that you can also, if there's some method that expects a spore, you can also pass a function literal to it. So a function literal is not a spore, it's a function. And there are ways to implicitly convert your functions to a spore, and then all of this compile time checking kicks in on your thing that you passed that was originally a function. So that makes the burden of writing these things a little bit, smaller. So here's an example where you might want to use a spore in an API. This is like sort of one of the main reasons for spores existing, because maybe it would be nice to have APIs that use functions. Like I want a distributed map, right? Therefore, I want, to take a function. It'd be cool. So here, So here, you just basically the signature instead of a function and whatever to whatever, a function of int to int, it's a spore of int to int, and that's it. And the checking gets sort of kicked in. There's also other ways to use spores. You can also use them in for comprehensions. And if you know anything about for comprehensions, you might know that they are desugared to calls to higher order functions, like map and flat map and width filter and these things. And that's what this little capture thing does here. Basically, it makes it so you can pass spores to these for comprehensions. And it basically makes sure that the spore checking is, for things that you use in your generator again, that those things are in the spore header, basically. So that's it. It's very simple, right? So what does it get you? So this is, like I said, this is the mainline version where it's mostly syntactic. It gets you, sort of the guarantee that, well, since things are evaluated upon, since the expressions are evaluated upon the time at the time that spores are created, spores are then like, you can think of them as being like function values that have immutable environments. So they're not going to do anything tricky over time, or you can just sort of depend on them always being sort of whatever they were when they were created, which is, often what we assume is the case and is not really. And then you also get to this environment being specified and checked, so you don't accidentally capture things. Like I said, unless you really want to capture Wikipedia, then you just write, okay, here, capture all of Wikipedia and send it over the wire. Go ahead. So I have this fun little picture about the comparison in my mind of spores when, you know, right after you create them and then when you apply them. So everything sort of gets initialized and you know what it is and what everything points to. That's not necessarily the case with normal closures. Things can change because all you know is that, you know, maybe you have a this reference or something, but, you know, over time different references might appear that you might be, you know, yeah, capturing. Your environment changes, right? So spores are always the same, and basically you have this crazy mess of things that kind of drags around your object graph in ways that you don't expect necessarily, or, you know, your users maybe do that, and you expect them, your users do this, and you expect them to do that, you know, and this is a problem. So then, yeah, what if you capture something like a socket? That's probably not a good thing either, right? Or, hey, let's capture an actor and send it over the wire. It's also probably not a good idea. So that's the sort of stuff that's in this research paper that I pointed out. So I'm just going to kind of run through a few cute little examples of situations you might want to prevent, but we do this with a type system instead of, you know, with the syntax. So if you, wouldn't it be nice then if you could add some kind of constraints that say, hey, I don't want a socket captured and sent over the wire, but in a way that's friendly and composable, so I can always just compose functions and never worry about sort of, you know, these constraints being lost or whatever. And that's one of the contributions of this research paper is that you keep track of the captured types at compile time. So you can actually, you know, there's this extra thing. Actually, we changed the syntax recently, or the name of this from exclude to without. But you can basically say, I don't want an actor in my spore. So if a user ends up then composing this function with another function and they accidentally capture an actor in their function, then statically this gets rejected. And yeah, so the important detail here is that you get this, it's all, we don't actually extend the types, like Scala's type system in any way. We just do everything with these refinement types. So we basically, you know, make concrete these type members here, one called excluded and one called, in this case, facts, which represent all the things that you capture in your function. So you can actually, in the type, know what is inside of your function from types. And just like regular functions, you have two operations. It's pretty simple. And then in compose, right? So you can compose functions. And the result type, so this thing here that I just showed you, this is always composed in a logical way, where you wind up taking, you know, for example, for the things that you capture, you always take the union, or for the things that you want excluded, you take the conjunction of excluded types. And then you have to check facts and all that to make sure that everything is okay and that you shouldn't reject this code, but, you know, that's basically it. So the point is that at the level of sort of the types that these things get, they all, you keep constraints if you have them. And so here's a cute little example where, hey, I have two spores and I want to compose them. The first one says, okay, I don't want to capture. This one here says, okay, I don't want to capture. I mean, this is all implicit. You don't actually have to. This is just for the sake of you visualizing what's happening. You wouldn't actually write this necessarily, but you know, basically, if you have some spore that has this type member as a, you know, don't capture an actor, and then here this guy S2 captures an actor, but doesn't want you to capture an RDE or an RDD, which is the distributed like list or array thing that Spark has. But it captures an actor. If you try to compose these things, then it will happily tell you, okay, you probably shouldn't do that. It's probably a bad idea. I can't remember this example. I think this one works. Anyway. So, what do type constraints buy us? So you get more than just checking and enforcing a shape at compile time. You get, you know, the ability to express these sort of strong constraints. And then frameworks are able then to make stronger assumptions about what users are doing and are able to be more helpful to users. And that also makes it possible to be a little bit more confident in writing an API that might be using these functions and passing them around in a concurrent or distributed environment, right? And you know, the cool thing is that you can also reason about these constraints in a nice way because they always accumulate in a monotonic way, and because you know of the way that they work, they're not ever lost when you compose them. Okay, so this is the part that I think is more interesting. So what would you ever want these for? Like when would you, like what are situations where you might want them? So I can easily imagine at least 4 cases, some of which do already exist, where these things are nice to have. So one thing, you know, which we all already know about is a framework like Spark. I keep on bringing this up as an example, so I'm not going to delve into a lot of details about it. But the idea then is that, you know, you have many pieces of functional, you have many pieces of data, and then you ship this function around and you apply sort of like this function, you know, or you pass this function to a higher order function and you apply it all over a distributed data set. Another idea is the idea of shippable like streaming pipelines. If you want to reconfigure something that's streaming, hypothetically you could, because now I can basically guarantee that some function can go from one machine to another, so I can change dynamically what some topology is doing. Another thing that you can do is you can dynamically hot swap the behavior of an actor. So, I mean, you can, you know, receive a message maybe with that contains a spore, and then make that become, you know, use the become operation on the actor and change the message handler that way, for example. And then another cool thing is actually you can make closures portable. So you can basically take closures that exist in Scala land, and you can using Scala.js, you can make them communicate with closures, or not necessarily using Scala.js, but you can make them communicate with perhaps a client or a front end of some kind. Because I already went through the Spark example, I'm just going to show you a few small examples of the other 3. Actually, the 4th one's a little bit bigger. So if you went to Victor and Roland's talk today, you might be familiar with these Akka streams, and you can, all right, so you can think of this as you have some kind of stream, and a stream is like a collection that, you know, takes streaming data in sort of an asynchronous way, and then it sort of pipelines things. So you can think of it also, again, sort of in like some like monadic sense, where you apply a function to like a chain of higher order functions, for example. So in this case, you know, you're doing a map. You're just transforming everything to uppercase on the data as it comes in, and then you're printing each line also as it comes in. And then, you know, this is just when it's complete, you just whatever shut down or something. Okay. So yeah, as I said, every stage has some sort of closure that it applies, or some function or something that it applies to the incoming streaming data. However, like I said, one could imagine that, you know, maybe you want to put the, you know, depending on your application, maybe you'd like a framework that puts these stages on different machines being closer to the data that you want them to operate on. Might be a good idea. But, you know, you also have the constraint that maybe you would like it to be assembled on one machine. You don't want it to be just assembled in some distributed sense. You want to assemble it in one place and then, you know, send these things around to the data that they should be near. So that then means that you're going to have to send the functionality that you have to apply to all of the data around in the same sense that Spark has to already. So in this case, how does Spores help? Well, they ensure that, in this case, of course, that the serialization errors don't always happen just based on user code that doesn't know what it's capturing. It enables also different serialization frameworks to you know, be used. Something I didn't mention earlier is that also the Spores framework, in addition to doing all this stuff with types, it's also based on type classes. So you can actually, like, if a certain type class is present, then some checking gets kicked on, right? So in this case, you can say, okay, an implicit pickler or something has to be present for that type for it to be serialized, of course. But you could also imagine that, well, you don't have to necessarily have an implicit pickler. You could have an implicit immutability checking thing. Maybe you can apply, since it's type class based, you can swap out sort of the type classes that then sort of apply some extra checking or functionality, like in this case, pickling. And then finally, Spores enable restricting types that are captured by each closure. So in the case that you have an actor sending around the functions that represent each pipeline or each stage, you probably don't want the user to accidentally capture it, right? So you can use these constraints again to prevent that. So if this is what it looked like before, it's actually, you know, not so bad to convert it to something using spores if the framework was used, was built using spores. So if you look before and after, you just have to, if you look at the map in the for each function, you just have to add this spore marker, if you want to call it that. You make this thing a spore block, and all of this checking gets applied. And then, as I mentioned earlier, there's this hot swapping thing that you might want to do. So say you want to receive a message that represents some different behavior, some new message handler. And here you might have some message called hot swap that receives a spore, you know, and this is the message handler of the actor. And receive in Akka, I think, is a type alias for a partial function. So what you have, since a spore is actually a subtype of a function, it's not a partial function, so what you have to do is you have to make it a partial function, which is pretty easy. Just do that. And you apply it. And then you just use this become construct to take this new behavior, this new message handler. And it's something, you know, as simple as that. It's not too convoluted to look at. And then the last example, which is a little bit longer, in my opinion, also maybe, you know, more interesting and very different than the others, is, say, you know, not big data, not, you know, like let's, you know, do another Spark sort of application. It's the idea that perhaps you have some sort of rich user interface thing that interacts with a server somehow, right? And if you have the situation where you have information that is fine-grained enough, so, you know, that has to be exchanged between the client and the server, you can actually use spores to sort of make things a little bit more composable and easier to extend. And I'll show you in just a second what that means. But basically, the high-level idea is that if you have selections in a UI, so like if you provide somebody with like a filtering pane, and then you want them to select a bunch of things to filter some, you know, out of some data set somewhere on some server somewhere, you can basically represent each of these selections as functions or as spores, compose them, so then you send the composed spore or function, whatever you want to call it, over the wire to the server and just apply that on the server side. And then that kind of makes things a little bit simpler in that there's no sort of, you don't have to be mapping like the, you know, fields and messages and things to you know, whatever gets applied on the server, to functions that are applied on the server. To make this a little bit more concrete, I'll show you a small example, basically like a search tool used for used car offers. So let's just say that you have a website where, like I said, you have a filter pane, and you want to filter out, you know, a bunch of cars out of a big data set based on things like price range or color or make or model. When all the preferences have been selected, you know, you want to send them, whatever they are, to the server, and then that does the filtering and then returns some kind of result. And some things that could be sort of simplified are, well, messages that might, you know, have a lot of filtering constraints or whatever you want to call them inside of it, or selectors in this UI, might get a little bit complex, which makes it maybe perhaps a little bit harder to, if you want to, say, add something like, well, I want to filter also by the number of owners the car has, maybe. So if you want to add new features to this filter, it could be you have to change code in multiple places, not only the UI, but basically the to and from, sending this data back and forth between the server, and then adapting the logic for this new preference on the server side. So there's a few places that you have to actually touch. And you know, if you do it this way where you start composing functions, the observation is that you can, you only really have to really change the UI. So you can define spores that are shared between the client and the server. And by the way, this works with Scala.js. We have a small like example of this thing, where basically each filter spore, or the spore that represents the user's like selector or whatever you want to call it, has a type like this, and this type looks like this because it's got to be composed, right? So then you go from so you have basically a spore or a function from pair to pair, where each pair is a car boolean. And it allows you then to define compositions of multiple functions or spores, and then, you know, for a car that matches like this entire pipeline or chain of composed functions, this is what's true, basically. So you take the second member of, or rather the second the second value in the pair, which itself is a pair. Yeah. And so this would be an example of one such like filter spore thing. So this would be for the price range. So if you have, your range is from and to, you abide by these SPORE rules where you make sure that these things are local because you do want to capture them and send them over the wire. And you basically do your filtering here. So this is your function, and this is your filter, right? And it's as simple as that. So then that makes it possible to do this composition on the client side. So on the client side, then you can sort of fold them all together into one user prefs, and then take that thing that gets composed all together and send that over the wire. You pickle it and send it over the wire. And then on the server side, you can just deserialize it or unpickle it, and let's just say you could even connect it to other frameworks, right? Like, so if on the server side you actually had, the world's largest car database, every car that was ever made, even like, custom cars people made in the garage, that's, the world's largest car database ever. You could use something like Spark, and you could basically, you unpickle your spores, your composed spores, so all of these filter spores or whatever, unpickled as user prefs. And then you just apply it to, in this case, maybe if it connects to something like Spark, or if it's a list or an array or something, you can just pass it to some filter and then, again, check for, the case when all of those filters are true. And that's basically another example that's maybe not as obvious as, hey, use it for SPORE or use it for Spark. Oops. And those are basically the examples that I wanted to show you. So Spores exist as an implementation described in the Scala Improvement Proposal 21. It actually was on the bottom of the slides, which I'll post right after this if you want to find it again. And it's also integrated, if anybody knows Scala pickling, this pickling framework that we built within the last year. It's also integrated with Scala pickling. There's a module so that Spores don't have to depend on Scala pickling. They can use any other serialization framework. But they connect to Scala pickling, so you can always use Scala pickling to serialize a spore. You can always use Scala pickling to pickle a spore. And then we've also implemented a subset of the type constraints that are described in this eQuip paper, which are also on a separate branch. And we should basically we should have this alpha version on Sonatype within the next day or two, or by the end of the week, but very soon. And actually, I think that's it. So if anybody has any questions, we have plenty of time. I think I'm 10 minutes early. Yep. So whoa. Okay. Blue. Yeah. It's actually, so the whole thing is implemented as a macro library. So we actually didn't touch the Scala compiler. And also another cool thing, it's in the research paper. I showed you these type constraint things, and you can make them much more interesting. Like I said, you can add like immutability checking if you implement an immutability checker, and then you can make sure that immutability checking is applied to your spores and all kinds of stuff like that, right? But all of this still, we haven't touched the Scala type checker. We basically found ways to kind of add extra type checking to things like spores, and all using usually macros. Okay. So that's also kind of nice, because then you don't have to wait for a Scala 212 or something. Yep. They don't, I heard until. Oh, like the actor, like the sender thing in actors, right? Or is that what you mean, like an unstable thing? Yep. Okay. Sure. So, oh yeah, I didn't actually show how you get rid of the sender. I probably should have. Because of this sort of constraint or this requirement on sort of declaring things that you need to use that you want to send over the wire, then you actually have to call the sender method in the case of the Akka example. So when the thing gets created, you basically call that sender method when it actually means the right thing, when you expect it to be actually that sender. And then it becomes, then you get an actor reference that is actually in the environment of the function that then gets serial, and everything works correctly. The problem is that if you wait over time, then that thing is different, and then you call it and you get something else, and you don't want that to happen. Yeah. So it gets put into the local environment. Yeah. That would, yeah, because you have to then assign it to something. Well, yeah, because it's a method, yeah. Well, you'd have to create like a val, whatever your result is, and then if you want to use that in your function, then it either has to be, so if you want, so in the function that you send over the wire, you either have to, it has to be one of the arguments that you pass, or it has to be this environment that you explicitly list. And in that case, the multiplication thing would be dealt with, because you have to explicitly call that thing and assign it to something and then reuse it, if that's clear. Yeah. Yep. Good question. So there's also another thing. It's in the SIP, but it's a detail that's like a little bit, it's like it's a little bit harder to explain very quickly in a talk. But so things also have to be. So if something is like a top level stable sort of path, so if it's like something in this like math object and you import it or something it's always accessible, then you don't have to actually make a huge environment of all those things. So if it's a stable path that's top level and whatnot, then you can be guaranteed that on every machine you have the same class. We assume that you have the same class files in every machine, so then you can always use it. Yeah. So, anybody else? Cool. Yep. Yep. Yeah, so are you arguing that it's better to say, like, instead of like, oh, I really don't want, there's like a million things that I don't want, and there's only like 2 things that I do want in this SPORE, right? And maybe it's more annoying to have to list them all. You're right. That's actually like something that we were debating for a little while. It's a design decision, and in the end, we figured that I think most of the time you're like, I'm Spark or I'm Akka, and it's probably not a good idea to serialize these 3 things. So this is just a. You could do it one way or the other. We chose the excluded approach, but one could imagine doing it the inverse if we didn't try. Yep. Yep. Okay, so yeah, I didn't show an example of this, but basically the thing is that you need to require, like, in the case of pickling, an implicit pickler for the SPORE. And that's some other, I didn't show that. I ended up just mentioning it kind of quickly, and I probably should have provided an example, but there's another sort of syntax that you have to use for that, and that's how you serialize things and whatnot, and it's how, you just have to basically make sure that there's a property of whatever, immutable of the thing, or pickler of the thing, and that's how it works. So it wouldn't be in the excluded or the included or the captured. So this is actually what this little, here, the second to last slide where I mentioned that we have this integration module. It basically just requires, it's like a thing that requires a pickler for any SPORE. It just, yeah. Yeah. So good question. So this type class-based thing doesn't do this deep transitive traversal, but the idea is then that if you want immutability checking, for example, or pickling, which they have to do that, so the pickling framework does that. I mean, you might just want to mark something as like this or that, and you maybe don't necessarily need this deep traversal. So for something like pickling or immutability checking, you would expect that logic to exist in the immutability checker or the pickling framework. Yes, exactly. Yeah. Yep. How do you handle exceptions? You mean, in what sense? You mean? No, we don't have any special, like, you know, we don't put tries and everything. You have to catch them yourself. But, you know, again, the whole point of these things are to hook them up to another framework like pickling. And for example, pickling does some exception handling for things that can't be serialized, and, you know, we put the effort there, basically. Or did you just?
Yeah. Have you checked how much this adds to the compile pipeline? Since I assume that it's a bit complicated to check.
You know, no, and the reason why is because it's not doing that much really. So we didn't actually check. Something like pickling actually does do a lot more compile time. Like you end up you doing this transitive thing, and then you're generating all kinds of extra stuff, and then you have to traverse things, and you know, we know what's going on, and there's a lot more typically going on for like an interesting class type or whatever in a framework like that. Whereas in this, it's pretty lightweight checking that's happening. So I can't say explicitly how much, but not much. It's not a lot. Yeah. Yep. We assume that everybody has the same class files. So we're actually not like hot swapping class files or anything. So that's also nice in some sense, maybe not if that's what you want to do, but like it's, you know, like nicer than all of this mobile code movement back in the day, because there's a lot less things you have to worry about, bad things happening, you know. Yep. Uh-huh. Yeah, so there are also, so just like everything has a specification, and like for example, you can't have like lazy values or things. So I mean, you know, yeah, there are restrictions about like what these things can be. They can't be vars, obviously. That would not make sense anymore if you're trying to avoid having a mutable, you know, environment. So there are a list of restrictions that are in the Scala improvement proposal that are written up spec style. So that kind of stuff doesn't happen. Okay. Yep.
Is there any way to constrain the code someone sends you? So like if you create a function in the browser and send it to
I showed this thing here where I put the constraints like in a, oops. Okay, so the first thing I showed you was here we have just like a simple spore that says spore from this to that. But because, you know, these are just, the spores with constraints are just refinements, you could also put, I mean, you know, your signature would be uglier and longer, but you could say, you know, spore int, then excluded, and then the member that you don't want. So then that method can never receive an actor, for example. You get it? Because since it's all just the normal type system anyway, and we already do this extra checking, like based on sort of the types and the constraints or whatever, you can put them in signatures.
So that would exclude any
so then if you're
code being sent.
so then if you have an API and you don't want somebody to send you, again, I'll keep using the actor example, you just make sure that in the signature you have an excluded thing saying an actor, and then any sort of user that compiles things with your library has that signature, and it rejects it because we have this extra checking, basically, because this is in the signature.
They can send that
They can send
a function that will.
Yeah, we don't do. Yeah, we're not doing like any sort of. We're just like we check the syntax to make sure it abides by a certain shape, and then we do this thing with all the types that the functions capture. We don't actually do any sort of like static analysis of what's actually happening inside of the function. It's all just types and syntax, shape. Yeah, we don't. So, but you could, somebody else could implement something that requires then a, whatever, a pure of something, a pure of whatever your spore is, in the same sense that you do it for a pickler or like this immutability thing, hypothetically. But I say somebody else can do that if you want to do the framework provides the ability to require that in the form of like by using type class instances. Yep. Uh-huh.
You basically check that the future doesn't capture some, for example, context or sender.
So you're saying, how do I, like, let me rephrase the question and tell me if I got it right. So you're asking, how do I send, is that like, how do I send something like a function to something and then have it have the spore stuff, or I didn't understand.
You're doing or of some, well, for example, can you enable implicit checking for of closures for example, like
Yeah, that's what we do. Yeah, well, so just normal functions then, right? Like saying closure is confusing.
in a specific place, for example, only in an actor.
So yes, basically, the thing is that then okay, so if you want the spore checking, you have to have it in your type signatures in your library. But the spore library that we give you does this implicit conversion, so you have the choice of either giving a function or a spore. But the library has to require a spore if it wants the checking. So the user can not have to actually write a spore if they don't want to, in some cases. Okay. Well, I see no more questions, so thank you very much.